Hello, my name is Reed Parsons. I'm a faculty member at the Earth and Geographic Sciences Department at Fitchburg State University in Fitchburg, Massachusetts. I'm doing this recording for the 52nd Lunar and Planetary Science Conference, which is a virtual conference, and I thought I'd do a recorded tour of my poster and share it with the meeting as well as the broader public for those who might be interested in this work. I'm doing this recording from my home, and I have 3 kids at home, so I apologize for any background noise during this video, but I am grateful for the conveners of the meeting for holding this virtually so that we can all exchange our ideas and research in a virtual format during this time. So my research addresses the formation of some ridges which are found on the flanks of the large volcanic montes which are part of the Tharsis region of Mars. So these deposits are thought to have formed during a time of an ice age during the Amazonian period of Mars. The Amazonian period stretches from about 2.5 billion years to today, and during this time Mars has been mostly cold and dry, but ice appears to have been redistributed from the polar regions to the equatorial regions due to changes in the obliquity, or the tilt of the rotation axis of Mars, which has gone between roughly 45 degrees and 15 degrees over the last 25 million years or so. However, what's unknown is what happened to that obliquity prior to 25 million years ago. The computer models for constraining the obliquity are highly dependent on some initial conditions, and therefore are fairly unconstrained when it comes to what the obliquity was like prior to 25 million years ago. So the object of this work is to use some observations of the surface geology of the fan-shaped deposit, which are located along the flanks of these volcanoes, to help to illustrate or provide an observational constraint on what the obliquity might have been in order to form these series of ridges that we find in the fan-shaped deposit. So the fan-shaped deposit, this is an elevation map of the Arsia and Pavonis, which together with Ascraeus make these 3 large volcanoes in the Tharsis province. Olympus, the largest volcano on Mars, is located here to the northwest, but these volcanoes extend up to 18 kilometers in elevation, and the fan-shaped deposit is outlined by the stippled line and extends for hundreds of kilometers to the northwest of Arsia, which is the largest of these fan-shaped deposits, and Pavonis is about 300 kilometers long, and these fan-shaped deposits contain a series of parallel ridges in their interior, but are outlined by a larger terminal moraine, or large ridge, that marks the margin of the fan-shaped deposit. Also found on the interior of the fan-shaped deposit are hummocky terrain, as well as a smooth unit, which looks to have indications of viscous flow, which brings us to the idea that there was a glacial ice deposit, which was flowing, deforming, and carrying debris to cause the deposition of these ridges, as well as a remnant of that ice, which is left behind to the modern day, which is represented by the smooth unit. So my work has been to simulate ice flow on the flanks of these large volcanoes and see how changes in obliquity can affect the dynamics of the ice flow. And what we found was, in a paper that we published in 2020 in PEPS, the Proceedings in Earth and Planetary Science, is that these pulses of ice which come in during high obliquity can cause a kinematic wave in the ice deposit, which, if it's overlain with some surface debris, which is coming from dust or a sublimation lag, that pulse of ice that's deposited during high obliquity will kind of bulldoze or pile up the debris that's on the surface of the ice and cause a deposition of a ridge at the margin of the ice sheet, which then will get overrode by the advancing ice sheet. And what was interesting about this work was that based on these observations from the fan-shaped deposit, we see that there are a series of parallel ridges which have been overrode by another set of parallel ridges. So there's one set of ridges which are oriented in this direction, and then another set which overrode those. And this indicates that there was more than one episode of glacial advance, and it also indicates that when ice overrides a ridge, it does not erode it away. And that's important because it opens the door to the possibility that these ridges are not being deposited during glacial retreat, which has been sort of the accepted viewpoint up until now, but instead were deposited during glacial advance. And so if we can preserve these ridges even after an ice sheet has overrode on top of them, it indicates that that ice could be depositing that ridge as it advances as opposed to when it retreats. So this is a reinterpretation for how these ridges form in the fan-shaped deposit. So here's a cartoon of this process where we have a sublimation lag forming on top of an ice sheet, which is cold-based, which means that there's no sliding along the base of the ice sheet. And when sublimation occurs, debris lag accumulates on the surface during low obliquity. During high obliquity, we have precipitation along the flanks of the Tharsis Montes, which occurs as air mass moves from the west to the east up the elevation of the volcanoes, causing cooling and precipitation. So when that precipitation happens, we accumulate ice. The ice velocity in the ice sheet accelerates, and that velocity will accumulate and pile up against the debris that is on top of the slower moving ice deposit, which is toward the toe. That will accumulate a large amount of debris in one location, which will be dropped at the end of the margin, resulting in a ridge. The ice sheet will then advance over that ridge, which will preserve it because of the cold-based nature of this ice deposit. And so each of these ridges could potentially be associated with one of these obliquity excursions in the Mars obliquity history. So here's an example of our model setup. It uses PISM, the parallel ice sheet model, which has been highly used in the glaciology community on Earth. And as far as we know, we're the first to apply it to Mars. We use the model in a flowline mode, which constrains the ice flow to a single sort of two-dimensional case where we have length and height. And we accumulate ice along the flank of Pavonis and allow it to flow along the flow line toward the north through the central part of the fan-shaped deposit. Here's a profile view of the flow line at different times, kind of during ice accumulation at this period between roughly 25 million years ago and about a 250,000 years after that in these two series of plots here. So the gray zone is where ice is actually accumulating, and you can see the mass balance here in millimeters per year. We get up to about 33 millimeters per year during high obliquity, and then during times outside of ice accumulation, the ice ablation rate is set at about 0.5 millimeter per year. Now that's fairly low, but that is what we would expect when we have ice covered by a centimeter or a few of debris. So here's just another figure from our 2020 paper illustrating this mass balance condition. We allow precipitation to vary with obliquity as well as temperature, which are indicated in these plots. So what's exciting about this is if we can tie a particular point in the recent obliquity history, the one that extends from 25 million years ago to today, during which we had, several kind of high obliquity periods which extend beyond the 45 degrees in obliquity that we would expect ice accumulation to occur along the flanks of these volcanoes, then if we can find that location on the fan-shaped deposit, that would allow us to calibrate what the mass balance conditions are required to reach that position at that point in time, given the modern obliquity history. Using that calibration, then, we could go back and look at the whole extent of the fan-shaped deposit and see which of these potential obliquity scenarios, this is from Lascar's work in 2003, we could, more provide constraints on which of these potential scenarios could provide us with the number of ridges and the extent of the ice sheet that we need in order to deposit the fan-shaped deposits and the series of ridges that are found in its interior. So that's our idea for a future proposal, and I appreciate your attention, and thank you very much.